Namaste and bonjour. My name is Srinivas Kaveri and I'm the director of CNRS Bureau in India. As you may know, CNRS, which is the French National Center for Scientific Research, is one of the largest and highly prestigious research organizations in the world. With a staff of over 30,000 scientists and engineers, CNRS in fact performs the state-of-the-art research in practically every branch of science. CNRS includes, amongst its scientists, 23 Nobel laureates and 12 Fields medalists. The main objective of our bureau in New Delhi is to enhance the cooperation between CNRS and research institutions in India. The present exhibition at IIT Bombay is made possible by the collaboration of CNRS with the French Embassy in India, and in particular with Dr. Olivier Fudem, Attaché for Scientific and Academic Cooperation in Mumbai. France and CNRS have enjoyed a highly privileged partnership with IIT Bombay. We are honored to be part of Techfest and proudly present the screening of 4 videos around the theme of robotics. The first video is about an ant-inspired robot which navigates on its own, copying the desert ant without GPS. Then you will meet Nina, the socially skilled robot. Nina understands not only our language, but even our gestures. The third video shows the science involved in the future of robots flying together so well that anyone can fly them without fear of crashing. And lastly, you will be invited to watch From Phantom Limb to Prosthetic Arm, a real boon for amputees. If you wish to have more information about these videos and the laboratories in which they were conceived, please do not hesitate to contact us. Thank you very much and enjoy the videos. Au revoir.
One little head, 2 eyes gazing skyward, 6 little legs, and for the first time for this type of robot, it knows how to get back to its nest all by itself.
So this robot is directly inspired by desert ants, also known as cataglyphus.
This little machine, on the other hand, is called Antbot, the robo-ant. It was born here at the Institut of Movement Science in Marseille, in the south of France. In this lab, scientists work at the crossroads of robotics and biology. Their mechanical creatures are directly inspired by nature. Their latest creation, Antbot, reproduces the behavior of the desert ant. Unlike other ant species, it can't navigate using smell.
Ants are highly efficient navigators, able to travel several kilometers, just like bees. They do this to gather food and then return to their colony.
This is the behavior the scientists were seeking to recreate. Their robot needed to be able to find its way home after taking a random path.
These specific ants travel along the ground. They have very few neurons in their brains, but they do have a visual system with surprising properties. Specifically, they can perceive light that is invisible to humans.
The bioroboticists developed new types of sensors so their robot could see the world just like an ant.
Here's the compound eye of Cataglyphus, the desert ant that inspired our work. You can see there's this upper part called the dorsal rim area that we've mimicked with the celestial compass here. Both act as instruments capable of determining direction during navigation.
This celestial compass that enables both the ants and the robot to have a sense of direction detects the polarized light from the sun, which is invisible to humans. Ants must also gather information on the distances they travel. They do this by analyzing the apparent motion of their environment as they move around, It's what's known as optical flow.
Dans une deuxième partie, on est allé mimer ce qui se passe.
On the second part of the robot, we mimicked what happens on the lower part of the ant's compound eye. It's the part that measures optical flow. So that's what we've done here with the MAPIX sensor that consists of only 12 pixels facing the ground. As the robot moves around, it senses the textured environment flowing underneath it. This provides information on distance to the robot. That way, it knows how far it has traveled since its last stop.
La connaissance de la distance qu'il a parcourue depuis le dernier arrêt.
To develop AntBot, the bioroboticists poured over years of research by biologists working to understand how insects navigate their environment. The biologists concluded that ants need 3 sources of information to keep track of their position in space: optical flow, polarized light from the sun, and they also count their steps. The bioroboticists made sure AntBot could sense all 3. They managed to show in a controlled setting that their machine could be as effective as a desert ant that can find its way home after exploring its environment. Both do this, of course, without using GPS and without relying on a powerful computer.
One goal of this project is to be frugal. We want to use a minimum of resources to accomplish very complex tasks. And that's what we've managed with the work we've done in bio-inspired robots. In the end, we need very few photoreceptors to pull off tasks that are known to current roboticists to be extremely complex.
So, being minimalistic has several advantages. First of all, the constraints force us to go places we would otherwise never go, to explore counterintuitive solutions, for instance. It often leads us to new ideas and new technological solutions. If we wish to create a robot that can travel outside without using GPS, it's a good idea to see how nature tackled the problem first.
This is an example of a robot mimicking a real-life insect, but it's a two-way street. Instructions for building a replica AntBot have been provided freely to the scientific community. These scientists hope that biologists will be able to use these robots to test various hypotheses concerning behavior of ants in the real world and contribute to a better understanding of just what it is that makes insects tick. Made of steel, small motors and an electric brain, this is Nina, and she's learning as fast as she can. Nina, a humanoid robot, lives at the GIPSA lab in Grenoble, where scientists are working to improve communications between humans and the robots that are increasingly finding their way into our daily lives. For the purposes of this study, Nina was given eyes, a mouth, lips and even ears to facilitate exchanges with her human counterparts. Although human faces are comprised of over 100 muscles, Nina's has only 10 motors. The team at GIPSA Lab is working to decrypt non-verbal communication and synchronize words with the movements that constitute the foundations of face-to-face interaction.
Obviously, verbal communication is an audio signal transmitted from my lips to your ears. But there's also a collection of gestures, looks, and facial expressions, combined with head movements that help get the message across. This is what we call co-verbal communication. And of course, there's non-verbal communication as well. Posture, the angle of the face, etc., which are influenced by the person I'm addressing, but also speak more generally to my emotional and physical states, my age, health, and so on. When combined, these signals make up the foundations of face-to-face human interaction. So our goal is to take these forms of expression and the way we decode them and impart that understanding to our robot.
After studying the mechanics of synchronizing movements to words, the scientists created a test that takes the form of a child's game. Placed opposite a human, Nina becomes a teacher and asks her partner to take a colored cube and move it. Working towards a goal, watching her partner, and using intonation allows Nina to improve her gestures and overall capacity to adapt when faced with complex situations.
The idea is to incorporate the fundamentals of social interaction into Nina's functioning. Robots on assembly lines in factories are already doing repetitive tasks in pursuit of a goal. What we would like is for our robot to be able to approach us in nuanced yet repeatable manners. In other words, accomplish the repetitive tasks of social interaction. We hope that the robot can look at us when it needs to, assess goals within an environment, and identify them in a way that feels natural. The robot itself isn't the end game for us, but rather another tool to better understand our fellow humans.
To help Nina seem as human as possible, the researchers must get inside her head, literally. From a control center next door, an operator wearing a connected headset can teach her in real time how to behave during a conversation. This immersive visual experience is made possible thanks to the cameras installed in Nina's eyes and the microphones in her ears.
Bonjour.
Hello, I'm Nina, the humanoid robot of the Gypsa Lab, and I'm currently being operated by Gérard Bailly.
The robot then replicates the movements of the operator's head. His eyes are tracked by his headset and mirrored by the cameras in Nina's eyes. This assisted learning is creating a database of behaviors that Nina will use as she confronts different situations.
This data will enable us to teach other robots in the future and demonstrate that a data-oriented task can be translated into things like dialogue, manipulating objects on a table, or even dealing with multiple people. Ultimately, how the robot should behave. Just as we teach children to watch and mimic adults, one could say that this robot isn't intelligent or autonomous, but is passively learning behaviors that will teach it to use its body.
Could Nina be the blueprint of intelligent behavior for the machines of tomorrow? As a tool, she remains a research platform with no function beyond these walls. However, the data compiled will be precious for roboticists, who are continually working to create robots that are adapted for human interaction. Robots that may one day master even the most subtle elements of human speech. The buzz of propellers, brilliant flashing lights and vibrating controllers. Gamers will soon be able to compete in a new kind of arena. Even as they disrupted the market, recreational drones still required users to undergo hours of training. Robotics researchers working in partnership with Drone Interactive have developed an app both fun and impressive in a gaming centre in the suburbs of Lyon. The Archidrone platform creates a game where 4 players can compete simultaneously, easily piloting drones even if they've never flown before. In order to make a game like this accessible to such a large audience, Drone Interactive had to overcome a number of technical challenges along the way.
We have 4 drones in a 25 square meter arena that is just 2.5 meters high. It's relatively small. If we were to put 4 manual drones in here with pilots who have never flown drones before, without a doubt, after 30 seconds, the drones would end in a heap on the floor. It was a serious technical challenge to come up with something more readily accessible. From 6 years old and up, people can play with this system. No collision is possible between the drones. However, you can still push the other drones around, which is a fun element of the game. They can't escape the arena as they'll run into their own virtual barriers. Imagine the drones surrounded by balls of energy, which prevent contact and the resulting crashes.
The arena is equipped with multiple motion capture cameras that record the real-time location of each machine. Controller in hand, the player manipulates the drone from a distance, but tomorrow they could be plunged into an entirely different universe. Archidrone is developing games using augmented reality. The player, equipped with special glasses, can see 3D game elements projected into their field of vision and then interact directly with the drones in the arena. In order to make all this possible, speed, stability and obstacle avoidance all rely on powerful algorithms. Drone Interactive has also collaborated with specialists in machine-human interaction. For the last 15 years, research teams at the GIPSA lab in the French Alps have been working on drone technology. The scientific problems include flight safety, drone control, obstacle avoidance, and even the vulnerabilities to hacking. They're creating algorithms for this alongside industrial partners. In order to efficiently prove their mathematical tools, the scientists are testing them against benchmarks within virtual simulations.
Our main interest is to be able to run a large number of tests and gather statistics on the algorithms we're using. It's something we just couldn't do outside because we don't have a massive fleet of drones to expand. Our secondary interest is in obtaining a more objective tool to analyze the results. That's to say that when we fly outside or in certain conditions, we can't compare what we did to what people would do in South America, for example. So the second advantage of the benchmark is to have something extremely repeatable and comparable.
After having validated their algorithms in a virtual universe, the researchers put them to the test in the real world within this indoor obstacle course. These drones, made in this same lab, need to follow a preset flight plan and autonomously avoid obstacles. It's a more cost-effective way of testing the algorithms before running further tests outdoors. As the world prepares for drones to deliver packages, secure sensitive sites, or even transport organs, researchers are rushing to explore all scientific problems linked to these autonomous flying machines.
One of the main problems with drones is autonomy, which is relatively limited due to battery usage. This limitation is one that our research will help lift by working not only on the batteries, but equally by using hybrid drones, which could improve flight times and load-bearing capacity. Even as we work towards applications like delivery, there's already a lot of talk. which means we have to be mindful of how the public will react to this technology. At the moment, we've mastered getting a drone to take off from one point and land at another completely autonomously. Unfortunately, we can't guarantee that it will avoid obstacles, nor can we be sure that if there's a problem en route, it will be able to find a safe solution given its environment.
As we wait to see drones evolve to fly autonomously through our cities, scientists are also developing the necessary legal framework based on what currently exists for conventional aircraft. One e-commerce giant has already announced their first home deliveries for 2020 in the US, delivering packages of up to 2 kilograms automatically within a 25-kilometer radius. One step closer to living in our science fiction future.
The robotic prosthetic limb, a seemingly ideal solution for those who have lost an arm to amputation. Even though technological progress has led to high-performance prosthetics, it isn't enough. The controls need to be more natural, and the actual manner in which they're controlled requires too much effort for many of their users.
We measure electromyography, or muscular electrical activity. By concentrating, the patient can control their robotic elbow. Then, once the elbow is properly positioned, they can send a signal to the prosthesis to say, I want to change what I'm controlling, and, for example, move their concentration to the wrist.
Much like a musical instrument, using a prosthesis like this requires a lot of practice, especially for people with amputations above the elbow.
It's already difficult for patients to learn how to flex their bicep or tricep alone, something that seems impossible because they usually contract at the same time in order to control multiple parts of their prosthesis. It's really difficult and can be frustrating in the moment.
So how does one control in a more intuitive way? A research team has found a particularly promising track. These robotics experts, doctors, and neuroscientists are studying an innovative, ambitious approach they're calling the movable phantom limb.
Ultimately, what is a phantom limb? It's the lingering sensation of a limb's presence after it's been removed.
We've recently demonstrated that over 75% of arm amputees feel their phantom limbs, sensations they can interact with, which means phantom limbs they can move.
When you put your hand on their arm, we're talking of course about what remains above the elbow, when they move their phantom limb, you can feel muscular contractions under your hand. Thus, the mobility of a phantom limb is demonstrated through these contractions.
If the missing limb is effectively a phantom, its movement still produces real muscular signals, even if the movements being carried out are complex.
It's amazing to see that when an amputee moves their phantom fingers, there are muscular contractions in the residual tissue. This doesn't happen in an intact limb. There's a hypothesis that suggests that after nerves have been cut, they will re-innervate the remaining muscle fibers in the arm.
These subtle signals from the phantom limb projected within the remaining tissue are what the researchers want to exploit. And rather than demand that the patient learns to use their prosthesis, they want to make one that would adapt to the patient's intent.
Can you lift the elbow? Open the hand? Relax? Make a rotation for me? The main objective of this project is to create algorithms capable of decoding what the phantom limb is doing in real time and follow its movement simply by reading the muscular contractions in the residual tissue.
What you can see on the screen are recordings of the data gathered from the participant. We placed electrodes along his residual limb and recorded them as they carried out a certain number of phantom movements. We'll enter this data into a self-teaching algorithm which will personalize itself to this individual, including learning what kinds of muscle contractions correspond to what phantom movements. It will be enough to adequately control the prosthesis.
As the technology is refined, comprehensive clinical attempts to control the prosthesis can be carried out.
The protocol for these experiments comes in two parts. The first, which wasn't filmed, consists of creating and training the algorithm to fit the patient. We filmed the parts of the test where the participants were in control of the prosthesis through moving their phantom limbs in order to complete the functional tasks in manipulating objects.
On top of enabling a more natural form of prosthetic control, these tests are creating a new constructive outlook on the idea of the phantom limb, which until now was simply considered a psychological side effect.
This removes a taboo. Often the response a patient would receive when talking about their mobility was, "You can't move something that isn't there," and the patients would worry that they were strange. This, I hope, will change with our study.
These promising early results have encouraged the team to continue their exploration of the phantom limb. Their study could one day enable